Hello, my name is Sarah Osborne, and I'm a product engineer here for ArcIMS here in Redlands, California. I'd like to welcome you to this training seminar on ArcIMS best practices, optimizing map configuration files. Today I'll be covering three general topics: best practices during authoring, modifying a map configuration file, and using log files to measure performance. The format will be I'll discuss the topics, and then I'll follow that with a review. At the end of the second and third topic, there will be a short software demonstration. Before we get started with the first topic, I'd like to talk about points to consider when you create a service. Creating a service is an art, and in order to optimize your service, you need to understand the environment your service will be used in. First, who's your audience? The map you're presenting must be appropriate for your audience. If the intended audience is anyone in the public, you may want to limit the number of features they see, reduce acronyms, and make sure they understand layer names. On the other hand, if the service is directed toward a small group of technical people, you may need to add more detailed layers specific for their needs. Next, the display media is usually a computer monitor, and the resolution is not as good as paper. Labels and symbols that look good on paper may not look good on a screen. But remember, these maps are interactive. This means users can click on the map to find out more information about features, reducing the need for as many labels. Third, display only the minimum amount of information needed at any given scale. It's very easy for a map to be too cluttered, so you should try to display only the features absolutely needed at any given scale. Again, you should consider your audience. Don't overwhelm your audience with too much information. Fourth, and perhaps most importantly, users have expectations of good performance when they access anything in a browser. You must always consider performance when creating a service. In fact, in many cases, performance is the overriding factor. Thus, it's important to consider performance with everything you do associated with a service. During today's presentation, you'll be hearing the theme of performance versus detail. You must balance how much detail you should have in the map versus how much time it takes to generate the map. I'll be talking today about the steps for creating and optimizing a service. It's important to understand the relationship between a map configuration file and a service. First, you need to create a map configuration file or document. Once you have this file, you use it as input to a service that runs on the ArcIMS spatial server. Once you have a service running, you can make requests for maps. When a service is running, you can monitor how long requests are taking for maps. Based on this information, you may want to further optimize your service for better performance. The first topic is best practices during authoring. ArcIMS supports two types of map configuration files. The first is ArcXML-based files. Since these files have an AXL extension, during this presentation, I'll be referring to them as AXL files. For these files, you use Author to create and edit them. You can also edit the files in a text or XML editor. AXL files are used as input to image and feature services. The second configuration file format is an ArcMap document. These files have an MXD extension and are in a binary format. You use ArcMap to create and edit these files, and MXD is used as input to an ArcMap image service. Today, I'm going to focus on creating ArcXML-based map configuration files as input to image services. However, many of the concepts I'll be talking about are also applicable to ArcMap documents. Setting scale dependencies on a layer is one of the easiest ways to improve performance. Scale dependency means that layers display at only certain ranges. As you are designing your map in Author, you should make the decision when each layer should be visible by setting minimum and maximum scales for each layer. When applied properly, Layers with more detail do not display until a user zooms in. You will find that there's a compromise between content and performance. More features means more processing. At each scale, you need to have a meaningful map with a minimum number of features. The other benefits of setting scale dependencies is that maps are less cluttered and less overwhelming to the user. Here's an example of a map at a small scale. It shows U.S. counties, cities, and major roads. At this scale, there's far too much information being displayed. A better approach at this scale would be to show only major features. In this map, only states, major cities, and interstate highways are displayed. In this example, users should be required to zoom in much further before more detailed cities, roads, and counties are displayed. I'd like to reemphasize how important it is to set scale dependencies. This is something you have complete control over to help improve performance. Another way you can make your maps more relevant and to improve performance is to symbolize your data appropriately for each given scale. When a map is at full extent or small scale, rendering should be as simple as possible. You should only use one color or symbol for the entire layer. As users zoom in, they may expect to see more features color-coded based on an attribute in the feature table. Symbolizing features in this way takes the spatial server more time. It must open the feature table and cycle through each record to determine which color or symbol to use. If you have a layer with thousands of features, this process can be slow. Therefore, you only want to use complex rendering when only a small subset of features is displayed. You should pick symbols which are appropriate for the scale. The more complex the scale, the longer it takes to draw. Also, a symbol may be distracting when the map is at a small scale. As an example, I have a map of parcels. At a scale of 66,000, all the parcels have the same color. As I zoom into 1 to 8,300, each parcel is colored based on the zoning type. At this scale, delineating parcels by color is more meaningful to the user than at a smaller scale. Another way to improve performance and reduce clutter is to minimize the number of labels. When a map is displayed on a screen, labels can quickly overwhelm and obscure important features of the map. Labels slow performance. The spatial server must take time to not only generate a label, but also calculate the best position for the label. More complex labels that use anti-aliasing or effects such as background glow can slow performance even more. Label as few layers as possible. Only the more important features on the most important layers should be labeled. Remember that in an interactive environment, users can select features using Identify to get more information about them, so it's not necessary to label everything. Labels must be legible when viewed on a monitor. This means labels are generally going to be larger than they would be on a paper map. Finally, as with features, you can set scale dependencies so that labels only display as the user zooms in further. For example, you could display a layer at 1 to 20,000, but not show the labels for that layer until a user zooms in to 1 to 10,000. In this example, I have maps where European cities are labeled. On the left, there are lots of labels, and the glow obscures much of the map. On the right, there are fewer labels, even though many of the features are still labeled. The map is easier to read because the labels aren't obscuring as many features. To review, best practices during authoring include use scale dependency, use symbols appropriate for the scale, and limit the use of labels. The second topic is modifying a map configuration file. In this section, I'm going to cover some things that you can do outside of Author. The output from Author is an Axel file written in ArcXML. This file can be opened in a text or XML editor. Once you open your Axle file in the editor, you can add, remove, and modify ArcXML elements and attributes. Author is a good tool to get you started to add your layers, set symbology, and set scale dependencies. But there's some things you can do outside of Author to help optimize your service. If you are unfamiliar with ArcXML and Axle files, this is a very simple example of an Axle file. ArcXML is made up of elements and attributes. The elements are always all uppercase. The attributes are always lowercase. Each attribute will have an attribute value inside quotes. You know this is a map configuration file because you see the config element. Inside config, you'll be most interested in the map section. Inside map, the properties for the map as a whole, such as the initial extender envelope, are listed. Next, all the workspaces are listed. This might be a connection information to ArcSDE or the location of shapefiles or raster images on disk. Finally, you have a layer element for each layer of the service. The layer has a reference to the data location in dataset and includes the symbology. In this case, we have a countries layer, which is made up of polygons. A simple render is used, so each polygon will be rendered the same way. When you save the Axle file to the spatial server and make a request to the resulting service, you get something that looks like this map. If you're unfamiliar with ArcXML, the ArcXML Programmer's Reference Guide provides information on all elements and attributes. This reference guide is part of the ArcIMS help system. It's also available on the ESRI Developer Network website. A best practice after creating an Axle file in Author is to add projection elements. While this doesn't necessarily improve performance, this is very important for getting your service to work correctly in many clients. For example, if you're using ArcGIS Explorer, you'll get an error message if no projection information is in the service. Other applications, such as the web mapping application created using Web Manager and ArcMap, may not be able to display your service correctly without the projection information, particularly if you're overlaying the service with data from another projection. You must add two elements, FILTERCOORDSYS and FEATURECOORDSYS, in the properties section of your Axle file. Each projection has an ID, and you must include the ID inside the element. You must also make sure that the envelope coordinates are correct for the projection. In some cases, you must also provide projection information for a layer using COORDSYS. Often, the projection information is built into the layer already. Most shapefiles have a PRJ file. Most layers in ArcSDE also have projection information. You'll have to add COORDSYS if you have file raster data in a different projection, or if you are transforming data from one datum to another, such as from NAD 27 to NAD 83. In this example, my data is in the Robinson projection, and the ID is 54030. The envelope coordinates are in the world extent for Robinson. And I'll be going over this in more detail during a demonstration. One way to improve performance is to include only subsets of data. You want to display only those features of interest to your audience. A data layer may have many thousands of features, but your audience may be interested in only a subset. Also, the fewer features that are retrieved, the better the performance. Remember, you need to balance the number of features with the performance of your request. You can select subsets of features for a service by using the spatial query element. You can set up a where clause that's similar to definition query in ArcMap. As an example, suppose you have a list of points of interest that fall on both public and private property. Your audience has access to only public property. Therefore, you don't want to show any features on private property. You can set up a where clause where only the features on the public property are displayed. To continue on this same topic, you can also limit the number of attributes. Depending on who your audience is, only a subset of attributes may be relevant for them. This improves in performance because both the spatial server and the client are processing less data. Once again, you use spatial query with the subfields attribute. Within subfields, you list only the relevant fields. Continuing our example from the previous slide, we expect our users are interested only in the name and address of the points of interest. I included both these fields as attribute values for subfields. You notice that I also included shape and ID. These two fields should always be included in an Axel file because the spatial server needs this information to correctly handle queries. While projection elements in spatial query are probably the most important elements you can add to an Axel file outside of author, there's some other elements and attributes you can add as well. For example, there's more elements and attributes available for both renderers and symbols. You might want to devote points in a layer using a true type font. You can do this outside of author using the true type marker symbol. There's additional support for geocoding as well. You can set side and end offsets in the GC style element. ArcIMS also supports a data extract capability. This allows a user to request vector data, which is returned in shapefile format. To do this, you need to include an extract extension. All these additional elements and attributes are covered in both the ArcIMS help and the ArcXML Programmer's Reference Guide. One final note, and this is important, once you make a hand edit to your Axel file, you should not open it again in Author. Author will sometimes remove elements and attributes if it's not expecting them. In this first software demonstration, I'm going to go through the process of adding some ArcXML elements to a map configuration file. Here's the Axel file that I'm going to use. It has 3 layers. There's a cities layer that's a shapefile, a countries layer that's also a shapefile, and as a background, there's a world image in GIF format. In the Properties section, note that there's no information about projections. This means that a client may not be able to use the service correctly. Some clients, like ArcGIS Explorer, may not be able to load it at all. I have a Send ArcXML utility, which can be downloaded from the ESRI support site. What I did here is I sent a get service info request to the service of the Axel file that I just showed you. And in the response, you can see that the properties mimics exactly what's in the map configuration file. So if there's no projection information there, there'll be no projection information here. This is the information. This is where a client will pick up information about projections. Now, you can find out more information about filter and FEATURECOORDSYS in a couple of places. The best place to go is the ArcXML Programmer's Reference Guide. At ArcIMS 9.2, it's included as part of the ArcIMS help system. In earlier versions of ArcIMS, the guide is a separate document. The first place I want to point out is this overview of projection elements. In here, you can get, you'll have a good understanding after reading this of how to use the projection tags. It also includes many examples on how to use them. I can also get specific information on the elements for feature and FILTERCOORDSYS. Now, I know my data is in Robinson for this Axle file, and I need to add filter and FEATURECOORDSYS. Now, if I don't know what the value is, what the ID for that projection is, I can go to this section here on coordinates, IDs, and descriptions. In here, there's a listing of all the projections. Now, I happen to know that the ID for Robinson is 54030. So I'm going to go ahead in the properties section and add this information. FILTERCOORDSYS ID equals 54030, and similarly for FEATURECOORDSYS. Once I make this change, I save the Axle file, and on my server machine, I refresh this. I refresh the service. Then when I go back to my send ArcXML utility, I'll send the get service info request again, and this time you can see in the properties section that my projection information is included. Here you can see FEATURECOORDSYS. Now I'm going to go ahead and send a request for an image. And if I show this, you'll see that you can see the countries and the cities. You'll notice that the background image is not there. And the reason is that this image is in WGS84. So I need to go ahead and add COORDSYS to the image layer. So I find the image layer, and I go ahead and add the COORDSYS element. Once again, I save my map configuration file, and I go ahead and refresh it on the server. When I send this request again, this time, the background image is included as well in the Robinson projection. The next thing I'm going to do is add spatial query to the cities layer in my Axle file. I want to include only those cities that are capitals. Now I happen to know that there's a field called capital, and any city that's a capital will have a value of Y. So I'm going to go ahead and add a spatial query. So I added spatial query, and my where clause is capital equals Y. I'll go ahead and save it and refresh it on the server. This time, when I make my request, only the capital cities are included in the map. So to summarize, to use the projection elements, you need to include filter and FEATURECOORDSYS in the properties section, and you may need to include COORDSYS in your layers. If you want to limit which layer you're going to see, or limit which data you want to see, you can use the spatial query tag. To review this section, map configuration files are written in ArcXML. More elements and attributes are available outside of Author. I discussed filter and FEATURECOORDSYS and spatial query. The ArcIMS Help and ArcXML Programmer's Reference Guide provides information on using elements and attributes. This third section is using log files to check performance. In this section, I want to discuss how you can use the spatial server log files to monitor how well your service is doing. The spatial server log files are a good resource because they contain information on what requests are made, how long it takes to process the request, and what the responses are. The log files are located in your ArcIMS install directory under Server Log. Before you can use the log files to monitor performance, you'll need to change the logging level to full verbose logging. There are several levels of logging. When you first install ArcIMS, the level is set to 2 by default. In this case, only errors and warnings are logged. For full verbose logging, you need to set the logging level to 4. In order to do this, you need to open up a spatial server configuration file named ImageServer.cfg, which is located in the server etc directory. You can open it in a text editor, then look for the log message level attribute. Change this from 2 to 4. After you make this change, you must restart ArcIMS. If you're unfamiliar with this process, information on changing logging levels and restarting ArcIMS is covered in the ArcIMS help. If you're using ArcIMS 9.2, you can temporarily change the logging to full verbose logging using Administrator. In this case, you do not need to restart ArcIMS. To do this, you open Administrator, and under the Tools menu, you select ArcIMS Logging. Once you select this, the Spatial Server, Application Server, Monitor, and Tasker log files are all set to full verbose logging. You should only use this method for short periods of time. Once the spatial servers are recycled, or the spatial server restarts for some reason, the logging level for the spatial server returns to the level stated in the CFG file. Once you have full verbose logging on, you can start using the log files to help monitor performance. This example is an excerpt from a log file for request to an image service. And here's how you interpret this file. Each request starts with begin request and end request. The first value you should look at is total request time. This value represents the entire request process from the time the spatial server received the request to writing out the response. In this example, the time took 2.172 seconds. Next, if necessary, you can review what the request was. Then, you want to look at some of the processing times for each layer. Data search time is the time to create and send a query to the data source. For this Europe layer, that time is 0.03 seconds. Data retrieval time is the time to process and fetch features. For this layer, it's about 1.02 seconds. You'll also see the number of features processed. In this example, it's 247. After all the layers are processed, there's some processing times for the request as a whole. The label engine time is the time to draw all labels. This service probably doesn't have any labels since the process time is 0 seconds. Total processing time is the total time after the request has been parsed until labels are drawn. Note that this time does not usually equal the sum of the prior times because not everything about generating a response is logged. Output time is the time needed to create the image. Once all the processing is done, the response is logged. Once you understand the components of a log file, you can use the information to help monitor performance. The first thing you want to check is the total processing time. In this example, it took 14.3 seconds to process the request. This is too long, and we want to look for the bottlenecks. Is there something taking excessive time to process? You want to look first at the data search and data retrieval times for each layer. In this example, the parcels layer is taking 1.6 seconds for the data search and 6.69 seconds for the data retrieval. This represents almost half of the total request time. If you look at the number of features, you can see that over 7,500 features were processed. It would be good to go back to the Axle file and either set a scale dependency for the layer if it doesn't exist, or to set the existing scale to a different value. In this service, I would also take a closer look at the streets layer. Should the scale dependency be reset for this layer as well? Maybe a different roads layer could be used at this extent that has less detail. Finally, I'd look at the soils layer. I would first determine if the layer should be visible at this scale. If it is necessary, I might look at ways to generalize the information at this scale. In this software demonstration, I want to show processing times for requests on a service that's not optimized and requests for one that is. This first application shows a service that's not optimized. You can see this map is pretty cluttered. There hasn't been a good use of scale dependencies, and the spatial server is processing a lot of features. The labels overwhelm the map. You can't see the roads, although I know they're there because I can see the highway markers. And the counties layer at this scale is too detailed. If I zoom in a little bit to the west, things look a little better, but the map is still busy for this scale. I'm unhappy about the number of labels, and many of them aren't readable. The second application shows an optimized service. It's using essentially the same data, but there's far fewer features being displayed at the full extent scale. Scale dependencies have been used for every layer. And in this case, you'll have to see that I have to zoom in quite far before I even see the counties. Once I do get to the counties, the number displayed is not overwhelming, and the labels are easier to read. Overall, the performance of this map is much better than in the first application. Now that you've seen the two services, we'll take a closer look at performance using the log files. Now what I've done here is I've made a request to the unoptimized map, to the unoptimized service, and I have an excerpt from the log file. You can see that the total request time is 1.28 seconds. You can also see here that a lot of layers were generated, and you can't really see a lot of them. If we go up here, the counties layer is taking 0.5 seconds in the data retrieval time. This is about half. This represents about half of the entire total request time. You can also see that 3,000 features were processed. This is a lot at this scale. Now there's some other layers here that may not be necessary. If you have the counties layer, you may not need the states layer or another layer called state border. And these redundant layers also take some time to process. For example, the state border takes 0.03 seconds. You can also see that almost 1/10 of a second was taken up in rendering labels. Now, 1/10 or a few 100ths of a second may not sound like a lot, but it all adds up, especially over many requests. In this example, if you were to remove the counties and the state borders and the labels, you'd have a savings of about 3/4 of a second, and that represents a large percentage of the total request time. Now I'm going to go ahead and make a request to the full extent of the optimized service. And you can see that it came up fairly quickly, and the total request time was just under 2/10 of a second. That's a significant difference for displaying essentially the same data. You can also see that there's far fewer layers Here's another example. This time we're zoomed into the West Coast of the unoptimized service. And this time it took 0.48 seconds, which is a little faster than the first time, but you can still see that there's a lot of layers being generated in this request. If I make a request to the same extent in the optimized service, you can see that a lot fewer features are displayed, and it took 0.156 seconds to generate this map. To summarize on this demo, you can use the spatial server log files to help you determine bottlenecks or slow-performing layers. You can use this information to start shaving off tenths of a second here and there for an optimized map using your data for your audience. To review this section, log files are very useful for helping you assess performance. You'll be able to look at the time for processing a request, and you can look for any bottlenecks on each of the layers. This concludes this presentation. For more information, there's additional resources that you can go to for learning more about ArcIMS. There's a virtual campus course called Learning ArcIMS, and there's a training seminar called Introduction to ArcIMS. There's also a couple of instructional series podcasts, one on defining projection information for ArcIMS services, and a tips and tricks podcast for ArcIMS optimization. Other resources include the ArcIMS Help, which includes the ArcXML Programmer's Reference Guide. For more resources, click What's Next in the list of links on the left. Your comments help us improve our seminars. Please take a moment to complete our survey. Click the Give Us Feedback link to take the survey. Thanks again, and goodbye.